seismics, the slowest velocity medium is the air, right? Okay, in fact, you get an air wave, but it's always the thing that comes in last. However, because in ground penetrating high frequency EM, the velocity is proportional to 1 over the dielectric constant, and the lowest dielectric constant that we have is in the air. It turns out in GPR, the first arrival is that air wave. And also, that first arrival is not attenuated because there's no electrical conductivity in the air. Basically, it's zero in the air. So, not only is the air wave the first arrival, but it's also the strongest arrival that you get, because everything that goes down into the earth and reflects and comes back up is going to have a lower amplitude than that air wave. So that's one big difference you have to worry about. So this first arrival, this seismic event that you see across the system, the section here, that's the air wave that's coming in first. The second thing is, it's often hard to generate refraction with ground penetrating radar. The reason being that as you go deeper in the earth, generally you get higher and higher moisture contents at a lot of times. And because the dielectric permittivity proportional to the moisture content, because water has the highest dielectric permittivity, what you get is, rather than an increasing velocity profile with them, like you often do with seismic, you get a decreasing velocity profile with them. So that means you just don't see refractions coming in. But this is an example. This is basically taking one of those roller systems that I just showed and rolling it over these different types of structures. This was kind of an example, a test to show the use of this for engineering or contaminant landfill characterization. And they just basically buried all these different things and then rolled the system over it. And so you see, you get these nice reflections off each of these objects. Why are they basically hyperbola? Did you talk about that in seismics? That a point scatter generates a hyperbola? No, you didn't talk about that. Okay. If you're going along and you're basically, let's just treat this as you're at the same point. So you have a shot here, you're going along the line, and you're generating a shot at each one of these points, and then making the measurement at the same point. Okay, so basically we're sending out an energy wave down and then measuring it at the same point. Okay, does that make sense to everybody? That's basically what these systems do. Even though they have two antennas, the antennas are so close together, it's like having the source and the receiver at the same point. Now, if you put an object down here, okay, and that's the only object in the subsurface, the distance, the wave will come down, it'll reflect off of that, and then come back there. And as you move along, basically, so you've got a depth, this, and you've got the distance, call that L, away from that. And for a uniform velocity, if you go through and plot the travel time, you know, the distance that this traveled is called X. Well, actually, let's use Z. Let's make this X. So the distance traveled by the wave going down, reflecting, and then coming back up is equal to the square root of X squared plus Z squared. Okay? And if you plug this in for the time, if you convert the velocity to the velocity to the time that it takes to travel, what you find out is the time that it takes to travel as you move across here from a point scatterer will produce a hyperbola. Okay, a hyperbolic-looking reflection. So these are basically then point scatterers, and they generate a hyperbola. Now, one of the things in seismics they do is something called migration. That reflection image that you measure here, and then migrates it back to the true position where that scatter, the origin of the scatter. One thing to note is right here you see this vertical barrel. It has a flat top, and it's the one example that actually produces kind of a flat surface, at least for a little bit. But that's basically how ground penetrating radar works. It's just it's analogous to a very efficient seismic acquisition system, but rather than using multiple offsets, you're just using one constant offset. And then
Wait, is that one of the, do you also get a velocity off those hyperbole?
you can analyze it just like seismic data. If you know the position, you could basically process the data assuming the point scatter and get a velocity.
Yeah, so you have depth on the right.
Yeah.
And that depth scale.
That depth
where
scale,
does it fit?
probably they just estimated the velocity of the medium just because they constructed this site and they knew the resistivity. You can do, if some systems allow you to move the antennas apart, so you can do a CMP to get a velocity profile. So, but those generally aren't used as much anymore. People just want to go out and make a measurement, find out where the reflections are, do whatever they need to do, and go home.
Exactly that time scale you're showing, that's an nanosecond?
It is two-way travel time in nanoseconds. So like I said, you have to make the measurements very quickly. Skip over that one. Here's another example, couple examples where ground penetrating radar was used to image fractures in the subsurface. Basically, hard rock applications, low porosity, very little fluids filling the pore space, so you don't have very much attenuation. And then you can generate images very well of things like fractures of caves, voids in the subsurface when you have these low attenuating situations. And then there was a big push back in the when this method came out. There was actually the oil industry did adopt it for a short while. I don't know how much more they're doing this, but they wanted to look at, we're often in the oil exploration business. We're often looking for basically old river channels, okay, large scale river channels that have high porosity and basically therefore might contain a lot of oil. Okay? But there was always one thing that the seismic images can't give. Information they can't give to us due to the wavelength of the seismic waves that are reaching down to that is the finer bedding within those channels. And so there was quite a bit of work that was done at one point in time going over outcrops where they saw these river channels and actually using ground penetrating radar to map the interbedded nature of those river channels, because the fines of the coarse grained sediments have slightly different porosities and water contents, so you get nice reflections off that. And here's a case where that was done. It's kind of hard to see due to the grayscale, but basically this was done over an old river channel, and you can see a high detail that the image produces of all those interbedded features. So you see, here's the base right down here. So this was some sort of bedrock or clay base or something like that. And then you have all these reflections showing different, different microscale layering that's occurring as the river channel was basically as deposition was occurring in the river channel, and erosion, deposition, erosion. So it's just a very interesting way to get high definition of stratigraphic sequences in situ. Now this was again a case where there was very fresh water, very low resistivity, and so there was not much attenuation in the waves.
I guess that answers the question. That's why the nanosecond is the order of magnitude much larger than the bigger channels. Because this is an order of
Yeah.
magnitude opposed to 10.
Yeah. this probably had very little water content. So you had tens of nanoseconds where this had high water content, so the velocity was low, but it was fresh water, so you didn't have attenuation. Okay, so that's ground penetrating radar. It's kind of like seismics, few subtle differences. Unfortunately, can only be used in the very near surface. Okay? Now let's move to other ways of making ground conductivity measurements. So as we move below say a megahertz, our EM field starts to satisfy, and this is all kind of explained in the note, in the handout online if you want to read that. Our EM fields